Okay, today we'll be looking at lesson 3-8, which is proof in algebra. Okay, so how to prove things in algebra. And the objective is the student will be able to prove statements in algebra. The vocabulary that you'll see that pertains to this, and we're basically on page 130 in our textbook. The first vocabulary word that they have in the first paragraph is theorem, and they define theorem as a statement that is shown to be true using a logically developed argument. So you're almost like a lawyer at the conclusion, and you're making your final remarks, and you bring together all your arguments and sequence them to such an extent that the jury is going to say either that person's guilty or that person's innocent, how you develop your arguments here. So you're trying to get, as a lawyer, to get them to where they would say, yes, what you say is true. So you have to develop a logically developed argument. And that's also what's called a proof. A logically developed argument that uses facts, definitions, properties, and other already proved theorems to show that this theorem here, this statement, is true. Now, the properties, you can look back in your textbook on page 45, and they have some properties there for addition and subtraction. There's another name for properties that you will see. Sometimes people will call these properties assumptions. So instead of saying the word property, they'll use the word assumption. And perhaps later on in geometry, you'll see the word axiom. So those are things that are assumed to be true, and you're not proving them. The properties, or the assumptions, or the axioms that you'll have in geometry. And no doubt each one of you has your good little red book of dictionary of math terms, and you can look up what an axiom is there. Now, the other word I have at the bottom here is algorithm. And I put that in there because we're not going to be using algorithms in proofs. You use algorithms to solve an equation such as x plus 2 equals 5, where you subtract 2 from both sides and get your answer x equals 3. You have a defined number of steps to do. There's a sequence to those steps, and we say that they're finite. We did 3 steps and then we're finished. We did 5 steps and then we're finished. That's what's called an algorithm. Unfortunately, there isn't really any algorithms to proving theorems. You have to sort of think about them and think about an approach to solving it, and then go ahead into that solution. So let's look at example number 1 on page 130, and look at its format. And you'll see that example 1, it says prove. So it says prove. Okay, this is what you're going to try to prove for all numbers a and b, a plus b minus b equals a. So it has for all numbers a and b, so for all numbers a and b, a plus b in parentheses minus b equals a. So that's the format that they have for the statement that we're going to be trying to prove. Okay, once we prove it, then we'll have a theorem that we could make use of. We could then afterwards say, as one of our reasons for all numbers a and b, a plus b minus b equals a is a reason for something that we do that looks like that. Okay. If we look at number 2, example 2, you'll see there it says for all real numbers a and b. So in example 2, it says for all real numbers. That's different from example 1 where it just says for all numbers. This one says for all real numbers, a and b. Such that a is not equal to 0 and b is not equal to 0. So in a statement like this, it almost tells you that you're going to be working with some type of proof which is dealing with a fraction setup. Somewhere in this proof you're going to have an a and or a b in a denominator, and therefore they want to take out those cases when they say for all real numbers a and b such that a is not equal to 0 and b is not equal to 0. So that's another way you can see a theorem, something you're wanting to prove, be presented. If you look over on the oral exercise 1 on page 131, so page 131, it presents us with another way that a proof statement can be provided. It says there, if a equals b, then, so if a is equal to b, then a plus c equals b plus c. Okay, so if a equals to b, then a plus c equals b plus c. So this is in the format of an if-then statement. The if part of it is assumed to be true. It's your given. So it's given that a equals b. What we're trying to prove, the statement then, would be a plus c equals b plus c. So you can see that the proofs can come in different types of formats. One had for all numbers a and b, the other one has for all real numbers a and b such that a is not equal to 0 and b is not equal to 0. And then they also can come in the format of if-then statements. If this is true, then this should be true, right? So if a equals b, then that becomes our given. Then we're trying to show that this is it follows from that. All right, so those are different ways it can be shown. Let's go back now to our example 1 on page 130. So for all numbers a and b, a plus b minus b equals a. And let's look at the statements and the reason. The first statement they start out with, statement 1, is a plus b minus b equals a. So in this proof, in this proof, we see equals a in this proof, we see them using the first part of the statement we're trying to prove. Right? They're using that part. And then they're introducing this concept here, right? And the reason that they're doing it, over here, this is a subtraction. And now by definition of subtraction, and the definition of subtraction is adding the opposite. So over here, if we wanted to put parentheses, we could parentheses, that would be a plus b, assigned b number. So now we're adding the opposite of the plus b here would be the minus b. And the reason you can do that is by the definition of subtraction. Now what they do is take this expression, and that becomes part of the second statement. That becomes part of the second statement. And then it has equals a plus b plus a minus b. So a plus b plus a minus b. Now, what does that look like? Well, it looks like they're making use of what we would call the associative property of addition. Over here we have A and B associating by being added, and then comes adding the negative B. Now what they've done is take that association and have it with B added to the minus B. So it's the associative property of addition. Okay, so you see how that they're trying to develop their argument. Then what they do is take out just this expression. The b plus the minus b equals 0. So b plus the minus b equals 0. Now, for what reason could they use for that? Well, if you remember back, there's the property for opposites. When you add numbers that are opposite, and I think that would be for addition and subtraction here. So adding opposites, so it's, if, for instance, a 3 added to a minus 3, the result would be 0. So the property is property of opposites. So we can see then that they've taken care of the b plus the minus b being 0 and the property of opposites. Now we come back to, in statement 4, we come back to this a plus b plus the minus b equals a plus 0. Now let's make sure. So a plus b plus the minus b equals a plus 0. Now what have they done here? Well, where they had the b plus the minus b, they're substituting zeros going in for that expression here, based upon our step 3. So this is by substitution. You can see they're developing the proof very, very logically, and there's not really an algorithm. I can't say, I do this, and I do that, and I do this, and I do that. You really have to think about it, and think about your properties, your definitions that you have, or previous theorems to make use of for this proof. So that was our step 4. Now what we're going to do is go to step 5, and we have a plus 0 equals a. Now that's looking in terms of, if you remember, that's the identity property for addition. And the identity value for addition is 0. Just like in multiplication, a times something equals a, the identity value there would be a 1. So here, the reason I can do this, a plus 0 equals a, is the identity property of addition. All right, now let's see where we're at. We're at step number 5, and now what they're going to do is really come back to our proof. And they're going to, their last statement's going to be, in number 6, is a plus b minus b equals a. Now, in our book, they say the transitive properties of equality. The transitive properties of equality. So what we're saying is we started out with this statement, that's equal to that. So that's, say, one statement. And then we worked with this all the way through till we got to a plus 0 equals a. So we really have then this here is equal to a, and therefore we put the a back up in here. That becomes our a plus b minus b equals a. So this then just becomes, they say, the transitive property. And that transitive property, again, is if it's, let's use some different letters. I equals j, and j equals k. Okay, then by the transitive property, I equals k. So we would have here, this would be my I, equals j, that's that statement. Here's my, this here, j equals k, but it's through many steps that we got to that, the j equals k, and now by the transitive property, I equals k, which would be what we were trying to prove originally. It also seems to me that you might use substitution, but I guess substitution in a sense is sort of comes from the transitive property. So there's not an algorithm. There's not hey, do these steps one right after another, and you're guaranteed to get to a solution. You're going to have to look at the problems and come up with your solution for them. If we go over to page 132, and let's just look at problem number 5 on page 132. So it's problem 5. So problem 5, 132, and by the way, sometimes statements, sometimes they'll use the word steps there, and reason. And the why they do that with steps is that the proof up here is something called a proof statement. So people might get confused between statement here and statement shoes down here, so they'll use steps and reason. But our book here uses statement. So let's look at number 5. Minus minus b equals b. Okay, minus a minus b equals b. So let's see the way they go through it. Now they do it within 5 steps, and I've specifically chosen problem 5 because of the last step that they have there. So the first statement in the proof is b plus a minus b equals 0. So their statement 1 is b plus a minus b equals 0. Okay, b plus a minus b equals 0. We saw this before, and if you remember before, that was what? The property of opposites. So a number added to its opposite is 0. 6 added to a minus 6 would be 0. In general algebraic terms, then b added to a minus b is 0. Now let's look at the next step that they have us go through in this proof. They go to minus b. They start out here with a minus b added to, now follow what they're doing here, equals 0. Let's see what they're doing here. They're starting out with a term which is minus b, and they're adding it to its opposite. So the opposite of a minus b is going to be negating that minus b. So they've put it all out here. Minus b added to the opposite of minus b, just like plus b added to the opposite of a plus b, which is a minus b. But they've written it all the way out. The reason for step 2 is the same as step 1. That's a property of opposites. Now let's see what they do here. There's step 3. You can see you couldn't really come up with an algorithm for this. You really have to sort of think them through. So step 3 is this one. Minus b added to, we're using step 2, equals b plus a minus b. So let me make sure that's right. So minus b is equal to b. Now what did they do here? They basically are doing, again, the substitution. B plus or minus b equals 0, above equals 0. So they're both equal to 0, therefore they're equal to each other. So this equals that because they're both equal to the same value. Now they use substitution here. You could also, I guess that would be in a certain sense transitive. I equals j, j equals k, although they're both the same. Therefore, they're equal to each other. So by the substitution principle. Okay, now let's look at step 4 that they have. In step 4, they're taking this term, minus a minus b, plus a minus b, equals b plus a minus b. So step 4, I'll make sure that, so they're taking this term, putting it here, this term, putting it there. These two stay the same. Now what happens when you take one term and move it to another place and move them around? Do you remember when you're moving, you're commuting. So it becomes a commutative principle. a property of addition. Definitely it's an addition thing. It's not subtraction or division, it's addition. Okay, now when they come to step 5, this is so neat. In step 5, they come and make the final statement, which is the original thing they're trying to prove. And you say to yourself, how in the world did they ever come up to that conclusion? Now here's an example. You'll notice in your textbook when it gives the given for it, it says proved in oral exercise 2. Well, actually it's not oral exercise 2, it's actually written exercise 2 on page 132. So right at the top of the page, you will see an A plus C equals, so if you'll see in problem 2, page 132 at the top, the theorem there is if A plus C, if A plus C equals B plus C, if that's true, then A equals B. Okay, so that's the theorem that you prove up in number 2. It's a previous theorem, so you can make use of it here. Now let's look and see what that means. Let me use a different color. If I go to step 4, this is your A plus C equals B plus C. Okay. Therefore, A equals B. All right, so you can see how they took, that was one of the reasons they did the commutative property up here, to get it positioned. So you see the minus a minus B is my A term, plus C, which is my minus B term, and that's in the same term position over here as the C, and then the B term is over here. So from step 4 to step 5, the reason they can say is, if you want to call it, we'll say it's actually problem, P-R-O, 2, page 132, which are actually problems under the written exercise, not oral exercise. So, this is like dessert. Proofs are like dessert. They're the fun things that you do when it's a rainy afternoon and you can't get outside. You come and look at some of these proofs and try to figure out how you can go from the first step, what you're trying to prove, down to your last step, and you've shown your arguments that are based upon the properties, definitions, or previously proved theorems can now prove this theorem. So that's it for lesson 3-8.